These are the notes for 1-1 and 1-3 for traditional geometry. So the first section just talks about patterns and inductive reasoning, and a lot of math comes from patterns and things people recognize as patterns and use those ideas of patterns to develop a bigger idea. So inductive reasoning is the reasoning based on patterns you observe. In geometry, we're also going to do a kind of reasoning called deductive reasoning, but that's not what we're in yet. So inductive reasoning, reasoning based on patterns you observe. A conjecture, think of that like a hypothesis. It's a conclusion you reach using inductive reasoning. I think because I saw this pattern that this is going to be the next thing that happens. That's a conjecture. This is the next thing. And then a counterexample, it is an example for which the conjecture is not true, where you've just proved something wrong. And I'm going to use all this vocabulary in these notes. So find a pattern. You can kind of see these, and I think you can figure them out. So what I'm going to ask you to do is push pause. Come up with the next two and kind of write a little description of the pattern, and then come back and check your answer. So push pause now. Okay, so you see I have them here. I know my diagrams here aren't exactly accurate, but I think you get the idea. It's a little difficult on the computer. But you can see, so I saw a pattern. I used inductive reasoning to determine the next number would be 48, 96, and 192. My conjecture was that this number would be 48 and this number would be 96. That's my conjecture, my conclusion after seeing a pattern of reasoning. Okay? So these two, find a pattern and use it to show the next two terms. I think you can do that one pretty well. In the next one, make a conjecture or like a hypothesis about the sum of the first 30 odd numbers. And then in the bottom, make a conjecture about the sum of the cubes. Remember, cube means to the third power of the first 25 counting numbers. So it would be 1 to the third, and then 2 to the third, and then 3 to the third. And you're looking at the sum of those cubes when you go from 1 to 25. So cube 1, cube 2, cube 3, 4 to the third, all the way up to 25 to the third. And the idea is not that you actually do it out to that number. It's that you look for patterns and things that may help you to determine a pattern to help you get out farther. Because that's the idea of math, is sometimes it just goes out so far. I don't want to sit and do everyone one by one. I'm looking for a pattern to make it easier. And you will see on the next slide, I actually do not have the answers to this one because I didn't want you to just watch and get the answers. So I'm going to ask you to work on that, push pause, work on that with the group at your table. We'll talk about this one, both of these tomorrow. But please push pause now and see if you can figure out a conjecture for each of these. Okay, in the next one, we're working with counterexamples. So I'm going to say something, and you're going to try and come up with a number or answer that proves the counter. So the square of any number is greater than the original number. So I walk in, I say, listen, the square of any number you do is always greater than the original number. And for this one, I know sometimes you might not be, kind of asking, what does that mean? I showed an example that works. Okay, so here I am, the square of any number is greater than the original number. And I say, look, if I take 2 and I square it, I get 4. 4 is the square, and 4 is greater than 2, which was the original number. This always works. And what your job is going to be is to figure out a counterexample. So you're going to try and find a number that when I square it, the result is not greater than the original number. So I'll let you work on that. I say, hey, you can connect any 3 points to form a triangle. You're going to try and find 3 points that do not form a triangle. Any number and its absolute value are opposites. Okay, so the counterexample would be a number and its absolute value that are not opposites. A number is always greater than its reciprocal. Can you give me an example of a number that is not greater than its reciprocal? And if a number is divisible by 5, then it is divisible by 10. So you want to give me this if part, a number that is divisible by 5, but I don't want it to be divisible by 10. That would be a counterexample, proving me wrong. So again, work within your groups and try to come up with these 5 counterexamples. So push pause now. Okay, these are the examples I came up, the counterexamples. For the first one, 1 would be an example. If you square 1, you get 1, and 1 is not greater than 1. Could have also used a half. In letter B, you can connect any 3 points to form a triangle. Well, what if the 3 points are lined up like this? This would not form a triangle, so that's a counterexample. Any number and its absolute value are opposites. What about the number 5? The absolute value of 5 is 5, and 5 are not opposites. A number is always greater than its reciprocal. Okay, well, what if I take the number 1/2? Well, the reciprocal of 1/2 is 2. 1/2 is not greater than its reciprocal of 2. And 25 was my counterexample for letter E. So you may have gotten different ones, and that's fine, but at least you have seen my examples as well. Some of these have several examples, a whole lot of examples. So that takes us through 1-1, and then we're going to go to 1-3. Okay, let me go back to the beginning on that one. Okay, so in 1-3 we start getting into geometry definitions. So we have point, space, line, collinear points, plane, and coplanar points. So there's 6 terms here. And you don't need a video to tell you what these are. So using the resources that are available to you, I would like you to define these. And please remember, a definition doesn't mean words. A definition to you may mean pictures. It may mean a combination of pictures and words. It's what would make this make sense. So you and your groups, I would like you to define these 6 terms on your own. So push pause, and however you want to do, define these 6 words. Pictures, words, combos, go ahead. So push pause now. All right. Now we're in some examples. We're going to try and use that vocabulary. So name 3 points that are collinear. Collinear, hopefully you learned, are 3 points that lie on the same line, and not collinear, 3 points that don't lie on the same line. And name the plane that's shown in 2 different ways. So again, these examples, what I'd like you to do is try these, put your answers down, look at these, kind of put your own answers down, push pause, and then come back and check your answers. So push pause now. All right, so these are the answers I got. I don't really know if you could really say that, sorry. The example of 3 points that are not collinear, you could have said y, z, x. There's a lot of different options on that. Plane shown in 2, as long as the points are not collinear. You can't have 3 collinear points and name a plane. Okay, so postulate, axiom, it's accepted to be true. We can't prove it. It's just kind of that makes sense, and we all just agree that that's the way it is. So I have some of these. So through any 2 points, there is exactly 1 line. So here's 2 points. Could you draw more than 1 line that contains both points simultaneously? And remember, a line by definition is straight. You can't have curvy lines in geometry. So that's just kind of accepted. You're like, yeah, there's only 1 line that could go through both of those. If 2 lines intersect, they intersect in exactly 1 point. That point right there. That makes sense. If they intersect, then that's where they intersect, only in 1 place. If 2 planes intersect, then they intersect in exactly 1 line. I kind of have a picture here. That's a kind of a 3D idea. In the module, I put a link to a YouTube video. It's like an under 2-minute video where the person actually kind of shows you in a 3-dimensional way, explains that a little differently, because that can be difficult to understand. Remember, planes go on forever. So when they intersect, it's not in a segment, they intersect in a line. What kind of points do they share? They share all these points in a line. And the last one, through any 3 non-collinear points, there is exactly 1 plane. With this one, I want you to know, if they were collinear, and I'll try to show this in class too, you could put a lot of planes through here, because you have to think 3-dimensionally. They're in the plane of the screen right now, but if you put a piece of paper perpendicular to the screen and through these 3 points, that would contain them too. Or what about one like kind of diagonally through? And we'll talk about that in class. All right, as we go to here, and actually I don't know if I have answers to this one. Intersection of planes HGFE. So I want you to try these, and then again, come back and check your answers. All right, for this one, I hadn't had the answers filled in. So we have HGFE. That kind of shows you it's like the top of the box. BCGF. And sometimes we name them with 3 points, 3 non-collinear, or 4, a plane. It's fine. Okay, well, what do they share? Those planes that go on forever. They share all the points that are in line GF. So you're going to say line GF. I'm actually going to jump out of this to write that for you. No, not yet. Okay. So this is your symbol for line. Line. G, I apologize. F would be the intersection. And you have to make sure this says line. It can't say segment. What is the intersection of plane HGC? So here's that plane. And AED. Okay. So their intersection would be line HD. Sorry. And the 2 planes that intersect in line BF, you could say GFB and EFB. There's a couple different ways, but I'm hoping you can see it's kind of the front of the box and the side. Shade the plane that contains A, B, and C. That would be this bottom one down here. And name another point that is not in the same plane as both points A, B, and C. So you see A, B, and C. A point that's not in that plane, well, you could say point F. You could have said point H. Just can't say point D. So please make sure you check the announcement. That was kind of a quick description, and we'll work through more of those ideas in this chapter.